Thank you. Well, it's very pleased to be here to celebrate Jean-Pierre's retirement. And the important thing when you go to a conference in honor of somebody is that he or she should understand the special lectures. So you should make it easy for them. And since I'm the first speaker, I'm going to set an example that I hope everybody else will follow, so that he can follow the lecture easily, he should enjoy it, and he should, if possible, be able to ask a question at the end of the test. And to set the tone right, let me start with telling a story. My favorite story, you may have heard it before, but it's relevant. The story is about the high school physics teacher who had a class. He noticed that somebody in the front row, perhaps called Jean-Pierre, was not paying attention. So he turned to him and said, Jean-Pierre, what is an electron? So the boy scratched his head and said, oh, well, I used to know, sir, but I've forgotten. So the teacher said, what a pity, quel dommage. Only two people in the universe knew what an electron was, you and God, and you've forgotten. So replace electron by spinor and you get the tone of this lecture. So what is a spinor? Now, I spent most of my life working on spinors in one form or another, and I don't know. Only God knows. Maybe Dirac, but he's no longer with us. So now Hermann Weyl was one of my favorite mathematicians, and he also wrote beautiful poetic language, English. And here is what a quotation he makes in his book on the classical groups, which I'll read for you. It's about he talks about starting off with the spin representation. He says, only with spinors do we strike that level in the theory of its representations on which Euclid himself, flourishing ruler and compass, so deftly moves in the realm of geometric figures. In some way, Euclid's geometry must be deeply connected with the existence of the spin representation. Now that is typical Delphic Weyl remark at the end. You have to think deeply to what he means. By the way, Weyl, you know, in their classical groups, he has this introduction which he apologizes that he's writing in a language not sung by the gods at his cradle. You know, he was German, but he wrote beautiful English, as you see. So now spinors, to be very mundane, remind you the basic algebra of spinors, and this is one way to understand it. You have the orthogonal group. Let's take an even number of variables, special orthogonal group, and in general, it's not a simply connected group. It has a double covering, which is called the spinor group. So double covering. Now the group, the complex. If you have a complex structure on 2n spaces, n-dimensional space, if you consider the special unitary group, the unitary matrices of determinant 1, this is a simply connected group. So this maps into the orthogonal group. Because it's simply connected, it lifts to the double covering. So you can regard the SUN as a subgroup of spin 2n. If you take any representation of spin 2n, you can restrict it to the subgroup and see what happens. Of course, an irreducible representation, when you reduce it to a subgroup, in general will become reducible and break up. Now the spinor representation of SO2n, spin 2n really, is a space, always talking about complex spaces, is of dimension 2 to the power n. And it breaks up in two irreducible pieces, S plus and S minus, half the dimension. If you pull this back to the SUN, then you find that the spin representation becomes the same as the complex exterior algebra of the complex vector space Cn. And S plus becomes the even part of the exterior algebra, and S minus becomes the odd part. And you notice that although S plus and S minus are irreducible representations of spin 2n, their restriction to the SUN breaks up and has degrees. But in the spin representations, there are no degrees. It's irreducible. Only under SUN do you see the degrees appearing. Now at the bottom I've also written the fact that if you take the spinors tensor the spinors, then what you get can be viewed as the exterior algebra of the complexification of R2L. Not assuming an underlying structure, complex structure, but also just forming the tensor product with the complex numbers. So these are the fundamental algebraic facts about spinors. Now, of course, algebra is not the whole of mathematics. And Hermann Weyl, you mentioned, talked about Euclidean geometry. And so it's geometry that I want to focus on. And the algebra just gives you the framework. But it's by no means explains what the underlying nature of spinors is. It just says, here's a representation of the group. Now, I want to focus on the comparison between spinors and the complex numbers. Complex numbers, you know, it took mathematicians several hundred years to really feel they understood what I was. I, the square root of -1, was called an imaginary number. It did not exist. But by finding it very useful, they used it in formulas, and gradually, step by step, it became accepted. And finally, the formal definitions were given. So I became, the square root of -1 became an accepted part of mathematics, but it took a long, long time. Now, I want to suggest that the spinors are analogously a square root, but they are the square root of geometry. Now, think about that. In geometry, the fundamental elements in geometry are undoubtedly to do with measurement, lengths, areas, volumes, and those are described mathematically by the exterior algebra, introduced by Elie Cartan into differential geometry as a fundamental tool to describe integrals. So that we understand very well. So what is the square root? Why do I say it's the square root? Because you remember that the tensor product of the spinors with themselves is the exterior algebra. So the spinors are, in some sense, the square root, not of one form of a given degree, but some of them all. So it's a very deep notion, and it'll take us probably at least as long as it took to understand the square root of -1 to understand what spinors are, and they've only been around for perhaps 100 years, so we are still in the very early days of the equivalent perhaps of the 15th century in terms of mathematics. And so I don't know the answer to my question, and neither does Jean-Pierre here. And I say maybe Dirac knows, but he's up there with God. So we are left on our own. And now if you have a complex manifold, if the manifold you're studying is complex, then it's well known from the work of Hodge and so on that the differential forms on the manifold can be broken up into the forms of type PQ, where P involves the dZs and Q involves the dZ bars, the mixture of the two, the product, tensor product. So when you have a complex structure, you see the square root, and the square root is complex geometry. So when you have complex geometry, you've found a square root inside the real geometry. The complex structure has given you a square root. But spinors exist without the need of complex structure. So what is a spinor when there is no complex structure? So that's really the question. And complex numbers are, of course, not important only algebra. They're important to geometry, and it was known, of course, early on that you could do, well, theory of Riemann surfaces was fundamentally developed by, formalized by Hermann Weyl himself. And so the important thing in complex numbers is the analysis. The algebra, square root of -1, is interesting. We know that the complex numbers are the algebraic closure of the real numbers. You don't need to keep going higher and higher up, just two equations of degree 2. But the really deep part about complex numbers is their role in analysis. Complex analysis, Cauchy's theorem, and all that. That's a very sort of unexpected bonus. When people started to use II in formulas, it was thinking only in terms of solving polynomial equations. But then, in the hands of the analysts, Cauchy and others, it became an indispensable tool. So that's where the deep part of complex analysis is. And similarly, you expect the deep part of spinors not to lie in the formal properties of representation theory, algebra, but in their geometrical meaning. Okay, the question is, what is the and geometry here I identify like Jean-Pierre with analysis. You do geometry on curved spaces, you have to use analysis, differential equations. So we have to, spinor analysis has to be found as a substitute for complex analysis. That's the first stage, going from Cauchy's theorem in this idea of the square root of geometry. Well, this problem was of course solved for the mathematicians by the physicists. Dirac introduced the Dirac operator in studying the wave function of the electron. And I'll come back later on to his motivation in doing that. But basically it's a Lorentz invariant first order operator, and it plays a fundamental role in modern physics. And the Dirac equation is the equation that he wrote down. And so mathematicians can learn from that. Now, the first step you have to learn going from physics to mathematics is that the Lorentz metric is a signature with a -1, and in Riemannian geometry all the signs are +1. So they're very different types of equations. Hyperbolic equations become elliptic equations. But in fact, this step of going from physics to mathematics to replacing the Lorentz metric by was already done by Hodge. Hodge's motivation in developing his theory of harmonic forms was Maxwell's equations. Maxwell's equations are the equations of electromagnetism, and Hodge took the same equations, applied them in Euclidean or Riemannian geometry, and developed the theory of harmonic forms, which, as you know, has been fundamental in the development of modern geometry, modern algebraic geometry in particular. So similarly, mathematicians, and here I enter the scene as I was a graduate student round about in the 50s, and interestingly enough, my supervisor was Hodge, and his colleague in the next office was Dirac. They were in the same department for 32 years, and they never spoke to each other. Not mathematically. That's because Dirac never spoke to anybody. If in other words, the transition from Maxwell's equations to harmonic forms was made by Hodge with great, profound implications. The transition from the Dirac equation to corresponding mathematical equation was not made by Hodge or by Dirac, and was left to people like me and Singer to. If Hodge had spoken to Dirac, I would have had no mathematical career. So we have to be grateful sometimes our supervisors don't talk too much to each other. Now, so the Dirac equation in Riemannian geometry, and it works not in flat space but in curved space. Again, we learned this from the physicists. You can look at the equation for harmonic spinors just like you can for harmonic forms. They are the solutions of the equation Dirac flight of phi equals 0, but equally well you can think of it as a solution of the second order equation d star d phi equal to 0. The solutions on a compact manifold are the same. So these are harmonic spinors. Now harmonic forms played a fundamental role in geometry, and the reason is Hodge's beautiful theorem that says the harmonic forms, the dimension of the space, is independent of the metric you choose. As you vary the metric, there are no jumps in the zero eigenvalue of this operator, which in general you expect. But for the Hodge operator, there are no jumps, and the harmonic forms always have the same dimension and give you the Betti number. It's topological. So the question was, is something similar true for harmonic spinors? First question one asks. And the answer is no. You start off in dimension 2. In dimension 2, the Riemann surfaces have a complex structure. You can analyze everything in terms of complex structure, and you find the space of harmonic spinors does depend on the metric, but the dimension lies in a bounded range between 0 and the genus. So that's already some information to give to the genus is the upper bound. But if you go to dimension 3 where things change, then Nigel Hitchin, who was at that time a student in Oxford, I suggested to him it would be interesting to work out what the harmonic spinors were in dimension 3, some suitably good example. And so we took an example of a sphere with not standard metric but slightly deformed metric, and he computed the space of harmonic spinors for these metrics. And what he found was that this dimension is unbounded. Unlike the Riemann surface case, it can go on and on, increasing forever. Explicit formulas, implicit values of the metric give you bigger and bigger dimensional spaces. So it looks like there's no particular role for harmonic spinors. They don't give you any information of a topological kind like harmonic forms, so it's a bit disappointing. That's the conclusion you get from such a preliminary investigation. But if you dig more carefully, you find there are topological significances. So the first result, and this result was in fact what I did with Singer and was motivated by the work of Hirzebruch before, and I put Hirzebruch question mark, not because I had a question mark about his work, I couldn't remember the exact date. But anyway, Hirzebruch discovered early on that if you have a manifold of dimension 4k, then it has all these invariants called Pontryagin numbers. If the manifold satisfies the condition, it's oriented first, it's compact, but if in addition second Stephen-Whitney class is 0, then a particular combination of Pontryagin numbers called the A roof genus is an integer. It's called A roof because originally he defined something without a roof, which was an integer, but this was a better one. And his conjecture was that this should be an integer. He proved the form indirectly that it was an integer. But there was no explanation. Why was it an integer? Well, this is really the start of my investigation with Singer, and our conclusion was that using the ideas of Dirac, the Dirac operator, you take the Dirac operator acting, it interchanges the role of plus spinors and the minus spinors. It's an elliptic operator from one to the other. Its adjoint goes backwards. And so this operator has an index, which is the dimension of the harmonic spinors plus minus the dimension of the harmonic spinors in minus. And this number, the index, which is the difference of two harmonic spaces, is stable under perturbation of the metric. Whereas the individual dimensions can keep going up and up, they go up equally on both sides, and the difference remains constant. Now we're familiar with things like Euler characteristics, which have this great stability, whereas individual homology may change. Euler characteristic is much more robust. And in the case of Hirzebruch's Riemann-Roch theorem, if you have a complex manifold, and particularly let's take the particular case where the first Chern class is 0, so-called Calabi-Yau manifolds, then the Hirzebruch-Riemann-Roch theorem says that the Euler characteristic, the sheaf of holomorphic sections, is topologically invariant, the arithmetic genus, and that agrees exactly with the index of the Dirac operator in this special case. So the index of the Dirac operator is given by a formula which generalizes the Hirzebruch-Riemann-Roch formula. The Todd genus essentially becomes the same as the A roof genus, and the reason the A roof genus is an integer is the same as why the Todd genus is an integer. It is the index of an operator, the difference of two dimensions. So this is a very satisfactory explanation of Hirzebruch's theorem, and it requires the hypothesis that the second Stephen Whitney class is 0, and that, which is where the spinors are hidden, because the W2 equals 0 is the condition that the manifold structure group lifts to spin, and therefore that the Dirac operator can be defined globally. In general, the Dirac operator can only be defined locally. And then shortly after we, something's gone wrong here, the orders, let me just, Shortly after we proved, the same year, it was observed by Leknerovich, who was a differential geometer in Paris, who was closely interested in relativity theory, and he'd known about the Dirac operator in relativity theory. He knew that he could define it on a curved background, and so he was in a good position to make this application. So the theorem of Leknerovich is that if you have a manifold, now ordinary Riemannian compact manifold oriented, if W2 equals 0, and if you assume the manifold has a metric of positive scalar curvature, it's a very weak condition, only the scalar curvature positive, then this number A roof M is 0, topological consequence. For example, if the manifold is 4-dimensional, this is the first Pontryagin class is 0. This is a rather strong, surprising theorem. And the proof is one line. If you know the geometry, you can compare the Dirac operator times its adjoint with what you call the covariant derivative followed by its adjoint. The covariant derivative involves much more than all the derivatives. The Dirac operator involves part of them. And the difference between the two, in general, would be complicated expression in terms of the Riemann curvature, involves only multiple of the scalar curvature. And so it's true, since the covariant derivative times its adjoint is always non-negative, if you add a positive quantity, that strictly positive operator has no solutions. Therefore, the conclusion, the Dirac operator has no solutions, either plus or minus, the index is 0. So it's a very beautiful, simple consequence. This, by the way, is a idea going back to Bochner, who applied it in the case of differential forms, but it's easier in the case of spinors. And then a few years later, Fritz and I discovered another rather striking geometrical result, which was again you assume this W2 is 0, the manifold is spin. Now you assume there is a non-trivial circle action. Some compact group, just a circle is enough, acts non-trivially on the manifold. Non-triviality means not all points are fixed. Then the conclusion is A roof is 0. Now this uses not just the index of the Dirac operator, but what we call the equivariant index, the index including the symmetry of the circle. In other words, when you have a metric invariant under a circle, you can always assume it's invariant under the circle by averaging, then the eigenspaces of the plus spinors and the minus spinors will decompose further according to the representations of the circle Fourier series. So for each Fourier component, you have an index, so you have a much more refined invariant. Anyway, the conclusion of the theorem is that this index the whole index is 0. The whole, and in particular, the constant term is 0. Now, this is a very strong result, and interestingly enough, the hypotheses are seen to be exactly relevant. If you take a nice class of manifolds which have symmetry, for example, the complex predictive space with its natural invariant metric, then you say, well, how about this? It has big symmetry. Why doesn't it contradict the theorem? Well, the answer is you see that the first Chern class is n plus 1 if complex predictive space has dimension n. N plus 1 times the generator. And this is, if this is congruent to 0 mod 2, the same condition as the W2 equals 0. So you see this happens only if n is odd. When n is odd, the dimension of complex predictive space is not divisible by 4. So trivially, the A roof genius is 0. When it is divisible by 4, it's on spin. So you can't, either one way or the other, it escapes the theorem. It is very nice, showing the theorem is sharp. Now the third, the next deep result about spinors is of a different order. This is the result of Seiberg and Witten. Now, I have to summarize here, but this followed the earlier work of Simon Donaldson, my student, who became very famous when, as a graduate student, he discovered the remarkable things about dimension 4. Fantastic news. Something opened up. 4-dimensional geometry suddenly became a much richer field, and uniquely in dimension 4. A few years later, Seiberg and Witten had a different approach to the same invariance of Donaldson, which was more physically motivated. Donaldson's work also had physical connections, but Seiberg-Witten was more physical, and it involved looking at not only solutions of the Dirac equation, but in dimension 4, you can write down an extra term. The Dirac equation is one equation for spinors, but you consider, in addition to the spinor fields, you consider what we mathematically call a line bundle with a connection. Physicists will call that an electromagnetic field. So for physicists, you couple the Dirac equation to an electromagnetic field. And this follows just from the algebra that you can get this coupling in dimension 4. You can square the spinor related to the curvature of the line bundle. So you get, and this is a quadratic equation, not linear, nonlinear equation. And the question is, can you solve these equations, simultaneous equations, the Dirac linear equation plus this additional nonlinear constraint? And this is the Seiberg-Witten equation, this pair of equations. And the Seiberg-Witten showed, very beautiful result, that if you want non-zero solutions for this equation for a given metric, then that puts a constraint on the possible Chern classes of the line bundle. The line bundle must take, Chern classes only have a finite set of possibilities. And those possibilities are then invariants of the manifold, differential topological invariants. These are new invariants of a manifold. They are the ones for which the Seiberg-Witten equation has solutions. So if you dig deeply into the Dirac equation with this extra condition in dimension 4, you get some fantastic new results. These new invariants really are translation of Donaldson's work in other language. In particular, it was shown by Witten later on that if you have a complex manifold, a Kähler manifold, then these classes are essentially reduced to the canonical class. And it's negative. So that somehow generalizes the notion of the canonical class of complex manifold to real manifolds. So this is where you go without assumption of complex manifolds. You get something analogous to, but much deeper. And this comes out of using the spinors in a very deep way. So this is a very, very deep result, and in some sense gets most use out of the Dirac equation. Now, a few minutes I have left. I'm told the timetable is very tight here, but I think we took 5 minutes at the beginning. So I wrote a paper a few years back with, when you get to my age, you don't try to write trivial papers. So you leave that to the youngsters. You try to write crazy papers, which might be. So our crazy idea was this. We wanted to introduce into physics the notions of not just differential operators, as usual, but retarded and advanced differential operators, the ones which depend on the past and retarded and depend on the future, advanced. And if you have one variable, it's easy to do. You just write down, for example, you consider a differential operator, you consider its value and its derivative. and then you write a linear relation. But in an advanced equation, you take the derivative at a different point. You translate it by some amount. Now, that you can trivially do and write down advanced and retarded equations like that, operators. But you can observe that translation has an infinitesimal generator, which is differentiation. So translation can formally be written as exponentiating a derivative. So if you want to translate by a, you exponentiate a times d by dx. Elementary, just formal retranslation of the notion. Now the question is, how do you define a relativistically invariant retarded operator when there is no preferred time direction? The whole point of relativity theory is you don't know where is time. So now the idea is, of course, that what you need is to use a first order operator, because that's what you need to exponentiate, which is relativistically invariant. Well, fortunately, Dirac discovered that for us. The Dirac operator was precisely invented by Dirac to find the first order relativistically invariant operator. And therefore, you could use that to define advanced and retarded equations formally. And we did that in this little paper, and we found by some elementary calculation with physics that the possible variables you can use, in this equation there are two variables, I call them alpha and beta, two constants, well, the second equation, alpha, seems to become, no, it's A that I'm talking about. A, the amount by which you multiply d by dx. This is related to a physical quantity called the Compton wavelength of the particle. So quantum mechanical notion is involved in deciding on the degree of retardation. So he thought this was a kind of interesting link, potentially. Now, by the way, here I'll make a little digression. When Dirac introduced his operator, his reasoning was that he wanted to write down that the Schrödinger equation was not relativistically invariant. He wanted to find the relativistically invariant. Therefore, he wanted a first-order equation. And he found it, and he wrote it down, and it was successful. But then a lot of smart Alex later on came along and said, what you see, Dirac wasn't clever enough. He could, in fact, you can do it with a second-order operator. You don't need to have a first-order operator. That was a mistake. He found this beautiful result, but he was mistaken. He could have done it without that. But these smart Alex were wrong. Here, I'm using, for this purpose, you have to have a first-order operator. You can't exponentiate second-order operator with the same result. You get something quite different. So here, for us, we really use the Dirac equation as invented by Dirac. And then we went on more ambitiously to say, well, what about Einstein equations, general relativity? Can we retard those in some sense? Write down a retarded Einstein equation. And we had some success, but only partial. And in this paper which we had, we did that. What we did was to use the Dirac operator acts on spinors. If you want something acting on forms, which is what you need to get to general relativity, you take the operator on differential forms, which is d plus its adjoint, little delta. That's an inhomogeneous operator, because one raises degree and one lowers degree. It acts on all the forms, like spinors. Now, when you square it, d squared equals 0, delta squared equals 0, you get the Hodge-Laplace operator, which preserves forms. And that's what Hodge did. And people emphasize the second-order operator, but first-order operator is more fundamental. But you have to have the view that it's sensible to consider inhomogeneous forms, and that's not very geometrical. See, it's the first step to spinors. Anyway, if you do that and write down the corresponding story for which we did before for the spinors, then you find that the scalar curvature this time gets replaced by the Ricci curvature, which was known to Bochner. And the Ricci curvature is, of course, what enters into the Einstein equations. So this at least gives you a bit of a clue as to how the Einstein equations might be retarded. And then you find that the other constant in the retarded equation, there were two constants. One was the degree of the shift, which we related to the Compton wavelength. The other was the size of the correction term, the retardation parameter, which they call beta. Now it turned out beta interpreted as the cosmological constant. So the same ideas which lead to quantum mechanics lead in the direction of cosmology. But this is a very incomplete paper. If you want to read it, you find that we don't quite know what we're talking about there, but it's okay. It's an idea. It's a crazy idea.
But not insane.
Not insane. I mean, well, I don't know. The line between sanity and insanity is a very thin line. Yes, my father wrote a book called The Thin Line. And here are some references for those of you who want to follow it up. I've given my paper with Hitzbrook on the Spinor index, my paper with Singer on index theorem, my paper with Moore on the shifted view, paper of Lichnerovich on harmonic spinors, the paper of Witten, which he really develops the Seiberg-Witten theory, and I should have included it in there, but it's got left out, Hitchin's thesis, which he calculates the harmonic spinors in dimension 3. So anyway, that's my quick summary. What is a spinor? Answer is we do not know. But we've learned that it has some deep geometrical significance, but quite wide has the significance. What it means and where that's going to go, we don't really know. The Seiberg-Witten equation is a very deep study of the link between, and dimension 4 particularly, between the spinors and geometry. And there is another approach, which is also in dimension 4, which I should mention, which is Roger Penrose's twistor theory. That is a way in which you can relate 4-dimensional geometry for special classes of manifolds to 3-dimensional complex analysis. It's a very beautiful theory which links these ideas in many ways, and there's another way of trying to understand spinors in terms of geometry, complex geometry, but complex geometry of not the dimension you expect, but of a different geometry. Anyway, I think at the end of my career, I like to leave some problems for the next generation. So, let me know when you've discovered what a spinor is, and I'll be listening from above. Thank you.
There is time for questions and comments.
Yeah, I start with a comment, if you allow me.
Yeah.
We mentioned very rightly the work of Nigel Hitchin about the unboundedness of the dimension of harmonic spinors.
Yeah.
The interesting point is that the metrics for which he finds that this is unbounded are the so-called Berger metrics. So as you know, both the director of IHS and my advisor. And these metrics are very specific in 3 dimensions. They are just obtained by looking at the 3-sphere fibered over the, if you want, the real projective line or complex projective line, or the 2-sphere. And when you shrink uniformly the length of the fibers, which are circles, then you get these specific Berger metrics. And that's exactly the ones for those for which Nigel just computed the dimension of the Dirac number, the kernel of the Dirac number. Now my question is, you, in a sense, as usually mathematicians do, you concentrated your attention on spinors of spin 1/2, as would physicists say. But some physicists have also shown that there is an interesting connection with the Einstein equation if you are looking at the Rarita-Schwinger operator, which is the analogous of Dirac for spinors of spin 3/2.
Yes.
Have you looked into that in some?
I know about this, but I haven't really looked into it in detail. But could I come back to your first point? I should say that this work of Hitchin, which shows that there are particular values where the dimension gets bigger and bigger and bigger, this actually has a topological significance. As I said, you don't get direct topological information out of the dimensions of spaces of harmonic spinors. But if you look at how the metric varies, how the spinor dimension varies with the metric, you find particular subspaces of the metric space of all metrics where the dimensions jump. And this you can relate to the topology. It has to jump. In fact, when you know the topology, you can predict that they have to jump. They have to be there because they carry topological information. What they carry is topological information not about the manifold, but about the group of diffeomorphisms of the manifold. The group of diffeomorphisms of the manifold is essentially a study of fibrations or of all metrics up to equivalence, and knowing when these dimensions jump, this gives you topological homology, cohomology classes in the classifying space of the group of diffeomorphisms. So there is topological information buried in exactly the sort of thing that Nigel studied, but it's not quite what you expect. It's different because there are jumps. The jumps are interesting. The examples are specific, but they're interested in the general theory, why there are jumps, what the jump mean, and calculating the cohomology of the jump. So the spinors have topological consequences in unexpected places. You have
Take the square root of Michael here.
yeah, that's known as taking the mickey. No, I think, I like to put it, the spinors are the square root of geometry. It's really sort of, it focuses attention on the depth of the problem, and if you think about the square root of -1, you realize that it takes a long time to... Understanding something is a very difficult notion, but you have to sort of ask yourself difficult questions, you have to pursue the geometry and analysis all sorts of ways, and at the end of a long series and of course I should say that the square root of -1 got its ultimate justification with quantum mechanics. Quantum mechanics showed you have to have complex numbers in probability amplitudes. And so you could say that the Dirac equation, which came before the mathematical application, already shows us that spinors have a deep physical meaning. Physics and geometry are, in my view, and nowadays accepted view, very closely related. So you don't answer that question just like that. But eventually, after lots of struggles and many centuries of work, a body of theory which will emerge and say, now we're beginning to understand what spinors are. But the time is, younger guys here in the audience may contribute, and we'll be here to see it. The next director, but 1 or 2 or 3 will be able to share a lecture where the answer is given.
If I may follow up a little on Jean-Pierre's question about the Rita-Schwinger spinors. Some physicists think that the real significance of these things is only revealed if you go to supersymmetry, that is, if you include also anti-commuting variables. And I would like to know whether you think they're on the right track, that this is the direction to go to understand them really and deeply, or this is a sidetrack for mathematics.
That's a difficult one. I myself have never been very enamored of supersymmetry in geometry. I feel supersymmetry is a very algebraic notion, and you just plug it into the geometry. You can do it formally. Physicists do it very successfully, and they have good physical motivation. And people are still looking for supersymmetry in the real world, the CERN experiments and all that. Myself, I have a slight distaste for them. But that could be personal prejudice. We all have to have prejudices, otherwise we can't pick and choose. I'm prejudiced against supersymmetry. But I recognize that a lot of my good friends use it very successfully. It's a very powerful technique. So I think the question is still open. My view is that, supersymmetry is closely related to exterior algebras. I think I postpone answering that question for the next century.
So maybe we thank